Hello everyone, I'm Richard Ren, a PhD student at Carnegie Mellon. Today I'm going to present our work, multi-objective path-based D-star Lite. Okay, in this work, we consider a path planning problem in dynamic environment while optimizing multiple objectives. So this problem arises in many applications such as autonomous driving, surveillance, and exploration. So very often we need to consider optimizing multiple objectives such as path length, path risk, arrival time. So we formulate this problem as a graph search problem. It's a multi-objective in the sense that each edge in the graph is associated with a vector cost rather than a scalar cost. And like when we optimize those objectives, we want to find the minimum cost path connecting the start and the goal location. Since we are optimizing vectors in general, there is no single solution path that can optimize all the objectives at the same time. Therefore, we seek to find a set of so-called Pareto optimal path. A path is Pareto optimal if we cannot improve over one objective without deteriorating at least another objective. And also in this work, the environment is dynamic in a sense that the edge cost vectors can change during the path following process. For readers that are familiar with D-star Lite, so in this problem formulation, if we have only one objective, then the problem becomes the one that is solved by regular D-star Lite algorithm. Okay, in multi-objective path planning, in general, between any pair of nodes, there are multiple non-dominated or say Pareto optimal partial solution paths. In the literature, there are mainly two classes of algorithms, node-based and path-based. For node-based approach, in each search iteration, they will select a node from the open list and expand it. And by expanding a node, all of the partial solution paths at that node will be extended to adjacent nodes. Another approach is path-based. Basically, in each search iteration, only one partial solution path will be selected from open and expanded. So in the literature, it has been shown that path-based strategy in general outperforms node-based ones. However, path-based strategy has not been evaluated in the dynamic environment, and this work aims to fill this gap. So here's the key idea. Basically, our strategy is to reuse previous search efforts. To begin with, we will search in a backwards manner so that the constructed partial solutions can be reused even when the starting node changes during the path following process. When the cost of an edge changes, we will first recursively find all the partial solution paths that go through this edge and delete them. And then we will use a new notion of consistency to find all the partial solution paths that need to be re-expanded. And then we will continue the search until all the cost-unique Pareto optimal solutions are found. And by doing so, we're able to reuse previous search efforts. In our test, we evaluate in different maps with different number of objectives. And to mimic dynamic setting, we add or delete obstacles in the neighborhood of the robot. So we have evaluated in several different maps with a varying number of objectives. In short, our approach MOPB star outperforms the existing node-based incremental search MOD star in all scenarios. In addition, our approach also outperforms searching from scratch on average. To conclude, in this work, we consider a multi-objective path planning problem in dynamic environment. And we develop a path-based multi-objective planner that can reuse previous search efforts to expedite the search after edge costs change. That's the end of the presentation. Thank you.